like to introduce to you today's webinar speaker. After about a quarter of a century, Dr. Alfred William Eustes III retired in 2021 as a drilling engineer faculty member and researcher from the Petroleum Engineering Department at the Colorado School of Mines. Prior to that, he was a field drilling engineer with Arco Oil and Gas. His recent drilling research work has involved experimental work with NASA's robotic drills for the Moon and Mars, NSF Antarctic deep ice drilling and coring, and other drilling projects. He has a joint appointment with the DOE's National Renewable Energy Lab, where he works with a team developing geothermal drilling improvements. Dr. Eustes has a bachelor's in mechanical engineering from Louisiana Tech, a master's in mechanical engineering from the University of Colorado at Boulder, and a PhD petroleum engineering from the Colorado School of Mines. And with that, I love your background, Bill. Welcome to the TOPCORP webinar season. We are thrilled that you're here, and I'm going to turn it over to you. Thank you for being with us.
You bet. Let me go ahead and start sharing my screen here and make sure that that works. Is that working for us now?
Looks good.
Yes,
okay,
looks
so
good.
you should see a slide that says drilling into the future. And as John pointed out, I've been in this business since 1978. I started with Arco Oil and Gas, and that puts us, what, 44 years ago. And I've seen a lot. I've seen a lot that's happened in drilling. I started off as a drilling engineer with Arco Oil and Gas. And what's really disturbing to me is that I took a bunch of students to the Permian Basin Oil Museum not too long ago. And one of the rigs that I used to work on back in the day is now a museum piece. A little bit disturbing, to say the least. In any event, let's see what's happened. And that is the focus of this discussion. And I might add, these are my opinions, these are my observations and so forth. These are what I see in this last 44 years, and especially the changes that have been wrought in the last 20 years, because we got to look back in history to see if we can drill into the future. So let's see what was going on. We'll start off with, in the last 20 years, it's been amazing, the shale revolution. That's George Mitchell put this together back in the Barnett Shale in the North Texas area, northwest of Fort Worth, Dallas. And as they say, it took 17 years for this overnight success to happen. What they did was they basically created a couple of technology changes. That's horizontal drilling. Instead of just drilling straight through, they actually turned it and went 90 degrees by oil field convention. The completion techniques that were used, the use of casing strings that were long along that horizontal section and so forth, the types of production equipment and so forth. And then finally, fracture stimulation. That is, we're drilling into rocks that basically had the same permeability, or actually less permeability, than sidewalks. And so the idea was to create these fractures that would be, in essence, a superhighway for the small little dirt roads being able to feed into the hydrocarbons into the reservoir, into the wellbore. What I'm going to focus on is the technology. I'm not going to look at the politics. I'm not looking at the issues of regulations and whatnot. I'm just going to focus on the technology that I see that will be the enablers and the continuation of those enablers as time progresses. Let's start off, though, by looking at the big areas that we see. This from the International, or the Energy Agency, the IEA, with the different types of reservoir areas, basins that are being developed today. We typically see, like, the big one is the Permian. That's where a lot of the oil and gas is being developed today. If you look at rig count, you'll see a boatload of them. The Niobrara here in Colorado and in Wyoming is a big area. Of course, the Appalachians with the formations there in Pennsylvania, Ohio, and West Virginia. The Haynesville, which is super hot there in North Louisiana, East Texas. The Eagle Ford, which was a big one that has been, I haven't seen as much of it as lately. And then the Bakken, of course, up in North Dakota is a big area where this shale revolution took place. And today we're starting to see more in the Anadarko Basin of Oklahoma. Now, one thing that I find interesting about this is if you notice on this slide right here from the IEA, the green represents the rig count, how many rigs are running. So you can see from about July of 2011 through about January of 2015, there's about 1,400 rigs running. And yet, if you look at the red line, which represents his production per rig in barrels per day initial, you'll see that they would make about maybe 200-300 barrels a day. Then, of course, the crash of January 15, coming back up a little bit to 900 through the 2018-19, and COVID hits and it really plummets. What's interesting is that the amount of production per rig actually continues to increase. And in fact, I don't know if we're post-COVID yet or not, but let's just say that the post-shutdown era, you're starting to see phenomenal improvements in production per rig. In other words, less rigs, more production. And the question is, okay, why is that? And is this a fluke? Well, if we look at the gas production, you can see the same sort of thing. You see the high volume of rigs and yet not real high production per rig. And yet we're down around at this point in July of 2021, you're seeing maybe 430, 40 rigs and yet much, much higher production per rig. So this is not an anomaly. What you're actually seeing is the focus of the technologies that we've used today. And this focus is going to be on horizontal drilling for our talk here. So what is it? What are the drilling enablers that have allowed us to be able to spot this shale revolution? And it starts off with drilling rig technology. It starts off with drilling fluid improvements and the way we've done that. The bit designs are amazing, and how we apply those bits have been phenomenal. The directional drilling control and its equipment have been a real factor in this, as well as drilling data analytics. I'm sure you've heard that before, as well as drilling management. So what we're going to do is we're going to focus on each one of these and kind of see where they stand today and where they may be heading in the future. So first question, what is a mad well? One of my good friends has talked about this. It's called a mad well. And it's like, what is that? Is that an angry well or is it an insane well? Actually, what it is a mile a day well. That is, they can actually drill 5,280 feet or more in one day. Amazing improvements in operations. So let's talk about drilling rig technology. And there's, as I mentioned, the first rigs I broke out in, they're now museum pieces. They were driven by, mechanical means. They had Kelly drive systems, which are mechanical. They're frankly, well, they belong in a museum. Today we have super spec rigs, which are basically rigs that have been designed to make drilling far more efficient. And they've got a lot of stuff associated with them. So for example, the power requirements have gone up phenomenally. What we see back in August of 2008, you see most of the rigs were in the 500 to 1,000 horsepower classification. That is the hoisting system itself and what kind of power was associated with them. Today, it's doubled, 1,500 to 2,000 horsepower. And so what we're seeing is a electrification instead of mechanical rigs, an electrification of those rigs. So typically what you'll see are diesel electric type of rigs. And then it used to be from DC, or rather AC to DC power. Today we're seeing AC to AC synchronous power, which is basically allowing for far more efficient operations of drilling rigs and more horsepower, more power, faster drilling. In fact, you put more power into a rock, you're going to drill it. There's no question about that. So it's been amazing, that change of electrification. One thing that's nice about electrification I can add is that if you don't have a diesel electric system, you have that, but you can also hook it to the grid, just straight into the grid and use that same power coming off of that to power the rig. And what's nice about that is it is a little bit more quiet in terms of, instead of having diesels running, you're just off the grid. Of course, you have to have the right locations for that to happen. Another thing that I think is fascinating about super spec rigs are the walking capabilities. If you notice in this picture right here, taken up in Wyoming, you see a whole series of wells in a line, and you can actually see them where they're stepped over to the side. That's because rigs actually have feet these days where they can push down, shove over, and then set down. So they can actually, instead of having to move and disassemble the rig and move it over and set it up, they can just simply, even with stuff standing in the derrick, they can actually pick themselves up, walk over, set down, and drill the next hole. Pick themselves up, walk over, drill, set down, drill the next well. In that respect, you can actually do what they call batch drilling, where you could drill a whole series of, say, surface holes, that first section of hole that have the same diameter, drill a whole set aside and walk back, and then drill the next section of holes, set them back, drill the last section of hole, whatever number of holes you got. And what's nice about that is it's got an amazing efficiency associated with that, be able to keep the same equipment, drill a bunch of wells, and then change the equipment out once instead of a whole bunch of time. So walking rigs are a big factor in the drilling rig technology enabler. Drill controls are really improving. It used to be, it was all mechanical. You had big lever arms and stuff like that you used to be able to control the brakes. You had throttle switches and stuff and all that. Today, it's almost all computer controlled, which means you have a lot more variability to be able to tune in the right values and so forth. And what's more, you have the information coming back to you so you can see what's going on. And what's really nice is you can record that information for future reference. You have an equipment right here where the rig driller is sitting there. He's got all this equipment around him to be able to see what's going on. He's even have video cameras. What's really sad is he's got something for his elbow so he doesn't hurt his elbow anymore. He doesn't have to yell anymore. He's got a microphone. Even has leopard skin type of a seat to sit in. It's pretty amazing, isn't it, for those drill controls? But this shows you one for an offshore rig. I look at this and it just amazes me when people say, oh, the oil field technology, that's old hat and all that kind of stuff. The answer is, no, it's not. Look at that joystick control, complete operational visibility, being able to see what's going on. It's amazing the changes in drilling control. They even let me one time on a H&P flex rig operate it. I'm just a drilling professor, and they said, there, go ahead, it won't hurt. So I actually ran the draw works to be able to lift the blocks up. And it's like they had a special device to keep it from me from banging it up in the top. It's amazing what they can do today. Pumps, you know, you got to move drilling fluid through the system. And back in the day when I was running rigs, if we had a 3,000 PSI pump, wow, that was big. Today, with all the different power users downhole, such as mud motors, the measurement while drilling tools, and so forth, you need a lot more power down there. And the way you do that is by pumping fluids at very high rates and at very high pressures. And the net result is you see a lot of 7,500 PSI mud pumps these days. So not unusual to see big mud pumps out in the field. The other thing that we see today is, as I mentioned early on about the hexagonal Kelly drive, which slid up and down while the device was rotating around it. Today, rigs have their rotation system that actually ride up and down with the rest of the rig equipment as it slides up and down. These are called top drives. And top drives can be electrical, they can be hydraulic, they run about 1,000 horsepower. Again, they can be infinitely variable. Instead of being fixed at some RPM or something, you can really dial in the numbers. And that makes a huge difference. And the other advantage is that you can continuously circulate, in other words, pumping fluid, even while you're moving the pipe in and out of the hole. So that saves a lot of issues there. So top drives is another drilling rig technology enabler. Another one is rig automation. What you're seeing there, that little red thing, that's a robot. That is what they call an iron roughneck. It's used to go and actually screw the pipe together or unscrew the pipe together without having to worry about trying to move that piece of equipment you see off to the left called a tong, which is a very dangerous piece of equipment. Today, it's all robotic. And because it's robotic, and you have the sensors to be able to measure what's going on, you can automate it. And so a lot of technology is being developed to automate a lot of these operations. Today, they have what they call drill-a-stand, where you can actually push a button and it will drill one stand, which you see on the right there standing up, automatically from the time you make the connection to the time you make the next connection. Pretty amazing, and it's continuing to improve as time progresses. Drilling fluids is another area of improvement. Now, in the past, it was pretty much either water-based or a pneumatic-based, which is basically air drilling, or oil-based. And I mean, when we talk about oil, we're talking about like diesel. Talk about a nasty environmental hazard. Well, chemical improvements have made drilling fluids far better. In fact, it's apocryphal, but I always think about 70% of the problems you get with boreholes is probably related somehow, some way to your drilling fluid that you're using. And so today we're seeing a lot more of, instead of an oil base, a true oil, crude oil or diesel, you're seeing a really highly refined synthetic, basically a linear alpha olefin or some sort of glycol mix or something that is far, far more benign to the environment and especially humans to be able to drill some of these holes, because some of these holes are really long. And when you go horizontal, you could be going out 15,000 feet or more, in which case, imagine if you were taking a piece of pipe and laying it down on a highway for 3 miles. And then I'm going to rotate this end and expect the other end to rotate along with it. Clearly, I'm going to have some sort of friction reducer. That's where the synthetics help, because the synthetics can act as a reduction in friction so that my torsion is not so high that I actually twist the pipe in half, or I can slide it along and be able to push it in position so that I got some force on the end of the bit to be able to actually drill. So pretty good stuff that they've got these days. Another thing we're starting to see, and our friends at the University of Texas, Austin, have been developing this, is drilling mud automation. In my day, you used to go out and you'd measure the thing. You'd have a little funnel, which was pretty worthless, measure a weight indicator and so forth. And you'd have to have a crew out there to do that. It got done maybe once a day. You need better control. So that's what this device is used, is to basically measure on the fly as you're drilling the different mud properties, the drilling fluid properties that you want to be able to keep track of in real time, such as your density, which is mud weight, your viscosities, your gas contents, and so forth. And so these are drilling mud automation systems to be able to measure that. And if you can measure it in real time, you can also record it. And that's another useful piece of information that we'll find out more about shortly. The other issue, of course, is in the back in the day, well, I keep talking about that, but it was 44 years ago, we had these giant pits. You talk about an environmental nightmare. You know, these giant pits would be there, and it would be where all the drilling fluid would wind up, all of the thread dope and oils and all from the rig would end up, as well as the tobacco juice from all the roughnecks spitting into the thing. And so the net result is it was an environmental nightmare. Plus, it's huge. Today, we're seeing what we call ZDS, or zero discharge system. Basically, they're designed so that it takes the drilling fluids and cleans them up. And what you can see is things like centrifuges, like these pictures right here, where they really knock out the smaller and smaller particles that you drilled up, the cuttings that come out, and be able to take those, dry them out, so to speak, dump them into a trough, as you can see in the left photo there. And then that has been cleaned up enough so that you can scoop them out and then land farm it or do some other environmentally benign disposal of those rocks. So zero discharge systems are also very small. You can see it's basically a truck with some of these sensors on it, or rather these pieces of equipment on it. So you can have much smaller environmental footprint. So that's a useful device, to say the least. The bits. You know, one of the big technology enablers that I see is the evolution of bits. Again, back in the 70s and 80s, trichomes were the king. I mean, they were like 80, 90% of the technology that was used in drilling, and they would last Well, if they last 120 hours, I'd be amazed. The development, though, of the polycrystalline diamond compact, or PDC bits, back in the 70s was actually designed by GE and the DOE, working on trying to come up with a better drill bit for geothermal drilling. And they weren't that good at that time, but since that technology changing, you started to see an improvement, and people started to saying, you know, these things are diamond bits. They should last a long time. And so what they would do is they would then design these bits specifically for a given formation so that they could drill efficiently within that formation. You can't have just any old bit drill any old formation and expect it to perform efficiently. You've got to tailor design it. One thing about tricones is they're really kind of tough to design because they're machined like that. PDCs are actually molded. So what you can do is develop the mold and then immediately change the design as whatever you want, number of cutters, the position of the cutters, the number of blades and so forth, and immediately change that relatively inexpensively. And these things can last a really long time. So what we're seeing is when you start drilling with this tricone, you'd have to pull the bit out every 100 hours, every 120 hours of drilling. Whereas with a PDC, they can last multiple wells as long as you take care of them. And you can drill 15,000 foot in just one trip. In other words, one time you went in, drilled that 15,000 foot, bring it out. Talk about a time saver. And so the economics of those bits, even though those bits are more expensive than a tricone, if you amortize it over the number of footage that the well that you have drilled with them, they actually come out cheaper. And today we're seeing the use of polycrystalline bits as being probably 80 to 90%. It's just completely flipped the tricone over PDCs. So that's one of the technology enablers that allows you to be able to drill long distances with long lasting bits that can be, you can drill quickly with because they've been honed in and specifically set for that. So there's a lot of modeling and testing that goes on with this. You know, one of the things we do in academia is we do a lot of finite element analysis where we break the units up into small, like little matrices that we can design specifically and look at the forces and the stresses and the cuttings and the fluid flows and so forth, like the computational fluid dynamics. The technology of computers has also enabled this evolution of bits. And the other thing I like is that at the end of the day, you can pull these things out, you look at them and you go, oh yeah, that one we got to do something different with. In other words, post-analysis. And by doing that, you close the loop for the design, the use, and then the post-analysis, and you go back to the design. And that has been an evolution. What we see for different types of bits and so forth is if you look at the penetration rate, the ROP, the rate of penetration and so forth, versus the stronger compressive strength type of rocks, you typically see the PDCs have actually expanded in envelope. Your typical steel tooth bit are fairly small or rather decent penetration rates, but they can't really get into these harder rocks. The insert bits, yeah, the penetration rate is a lot lower. They can get into harder rocks. If you get into really hard rocks, if you're drilling in geothermal, for example, typically you get impregs and natural diamond bits. But then the PDCs you can see are primarily more in the sedimentary rocks. You're starting to see them used off. They're much faster. What's interesting to me is I'm starting to see that right edge of that PDC start pushing more into the harder formation compressive strengths, which you're going to see with the geothermal operations coming up. When people are drilling geothermal, where I'm starting to see that pushed in that direction. Here's an example of a post-analysis. If you look, that's a real drill bit. That's a polycrystalline diamond compact. You can see the inside cutters are in pretty good shape. The outside cutters are pretty tore up. In fact, some are missing, some are cracked and so forth. That's probably a sign that this thing has been probably whirled. In other words, that it kind of spun like this, and that outside edge probably got the tar beat out of it. So what does that say? Well, that says I need to do a better job of balancing the bit as well as I probably have to speed it up because whirl is typically, because I'm not pushing harder on it. You know, I got to push much harder on that bit. How about the directional drilling? One of the things we're starting to see is improvement in drilling mud motors. Mud motors are devices that you put as part of your drill string right next to the bit. And as you pump mud through it, there's actually a rotor in there that has one, you know, as it spins, it has one less lobe than the stator it's in, which means it's got a gap in there. And that gap is a cavity that as it spins, it's a progressive cavity. So in other words, I pump mud in there at high pressure and it kind of pushes that rotor out of the way. And as it does that, it spins the bit. And that's where we need the power from the flow rate and the pressure to be able to get that thing to spin. Those mud motors allows us to be able to do directional drilling. And so if we take a look today at some of these mud motors, if you look at the one on the left, you'll notice it's got a stator, that's that black part, and a rotor, that's the silver part. Typically that silver is made out of metal. The rotor is, or the stator is made out of elastomer, and you can see the cavity in there. Today we're starting to see more on the right side, which is a metal to metal type. Because the stator is made out of rubber, you can actually pump too much and it'll just start blowing chunks of rubber out of the thing. Metal to metal's got friction problems. So, and plus it seals, you know, the seal is metal seals are a little bit tough to get. So if you look on the far right, you'll see what we were starting to see today, and that is mud motors that have like an elastomer. They're actually metal back, and they have an elastomer to be able to kind of seal around it. And what that does is it seals it, and yet it has the metal to back it up to keep it so that I can pump even higher pressures through it and get more power out of it. So we're starting to see that in the realm of mud motors. Here's an example of that conventional with the non-uniform elastomer versus the well, ERT is just a trademark name. It just pulled it to look at, but gives you an idea of that power section and so forth. One of the big ones that I see is the use of rotary steerable systems. And I'm going to back off that for just a second. Let me finish up with control. And that is one of the technology enablers is being able to measure what you're doing while you're doing it. You know, it used to be that you would drill and you would end up with, you know, basically kind of guessing what you were doing. Today, we've got tools down hole that measure what's happening. Which way is your bit pointing? Which way, or what kind of forces are you putting on your bit? What kind of rotational speed have you got? How hot is it? Which way, you know, which direction is it going and so forth? These are amazing technology enablers that basically is kind of like driving a car with your eyes closed versus being able to see where you're going. In essence, measurement while drilling is doing that. And more importantly also is to be able to keep a track of where you are within the formation. That's logging while drilling. By using gamma ray or other measurement techniques that have been around a long time. But in this case, the logging tool is integral with the drill string. So you're busy measuring the properties of the formation while you're drilling. So if you happen to get out of the formation, you'll know it. So you can turn it and get it back into the formation. Or in other words, geosteer your way through the system. And that way you can stay in the formation with logging while drilling. You may be asking, okay, how do I get these tools down there? Well, they're either set up as a probe. In other words, you lower a tool within the equipment. And so that way you can recover it if you ever get stuck or something. Or it's actually part of the assembly itself, as you see on the right there. And you'll notice that there is, in one case, you have a battery pack for power. The other one, you see it has a turbine with an alternator to keep the power going for downhole. So another power use of why you need those big mud pumps, to be able to pump enough hydraulic power down to be able to control these things. Here's an example of where you might be using an LWD tool. You've got the tool down there measuring the resistivity, the gamma ray, maybe the density and neutron if that's what you want. And you can actually, because you're supposed to know what you're in, right? You know the characteristics of what you're drilling. If you get out of that, you can just admit, oh, geez, I'm up high. I'll turn the bit and come back down, or I'll turn the bit and go back up, or whatever it might be, or if I cross a fault or something like that. So this helps me to tell me what I'm doing. The other thing you might see is telemetry options and so forth, such as basically what we see today is a lot of mud pulse telemetry where they change the pressure in the system. So the system is pumping mud at a relatively constant rate, has a fairly constant pressure. What this does is it actually causes pulsations in that pressure, so you get a pressure wave. And in that pressure wave, that allows you to be able to interpret whether you're dealing with, like, if you have a pressure wave up, it's like a 1, down might be a 0, down, back and forth, and you get 1 0 0 1 0 binary code. And using that binary code, you can then decode what the machine is trying to tell you. The future includes faster means, because this thing's, you get 40 baud out of it. You know, I mean, my PC Junior back in 1984 had a 300 baud modem. We get about maybe 40 baud, maybe better sometimes. But there are better tools out there that are being developed. You've got extra long frequency radio waves, which are kind of limited to the same baud rates, but it eliminates the need for pressure pulses, which was good for air drilling and so forth. Acoustic, people have been trying to develop acoustic, where imagine hammering on the bottom of a piece of pipe, bang, 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 and you hear the waves as they come back to the surface. You can listen for it. The signal to noise ratio is kind of low, so that's kind of tough. Wired pipe has been very popular offshore. We actually have a physical wire that goes down to the sensors and so forth that are downhole. The problem there is you can't have a connection, direct connect back to the surface, because you can't screw the pipe together. So what happens is when you screw the pipe together, it actually butts up against each other and they have an inductance coil. So they tend to be kind of pricey. Now the rotary steerable system, let's go back to that one. This is a big one that I see, and I think this is going to be a lot more of the future also. When it comes to directional drilling, I can sum it up fairly easily. You either point the bit in the direction you want it to go, or you push the bit in the direction you want it to go, and more than likely you do both. So that's what these tools are doing. As I mentioned with the mud motors, basically they have to be stationary relative to the borehole with the bit on an angle. So they sit there like this. So I have to orient that thing in the direction I want to go, and then push it as well as point it in the direction I want to go, which means I can't rotate. Well, that's a slide. They call that slide. But if I want to go straight, I just rotate the whole thing, and the bit's sitting there wobbling back and forth, and you're not getting a direction, any preferred direction for it. That's all fine and dandy, but if those of you that have a background in engineering probably recognize static friction versus dynamic friction. Static friction is like when I put my hand on my desk right here and I push, my hand doesn't go anywhere until I push hard enough and it slides. And then once it starts sliding, the friction goes down. That's dynamic versus static friction. Well, mud motors that are in slide mode have a lot of friction associated with them. If I could somehow continue to rotate my string, it'll be in continuous dynamic conditions. And so what I can do with that dynamic is basically push it further. Well, rotary steerable systems are designed to either keep the point of the bit as it rotates. In other words, it's kind of like the bit's pointing this way. And as you rotate, the bit's rotating backwards at the same speed. The net result is you're pointing the bit in the direction you want it to go, versus push the bit, which is basically, if you notice there on the right, you see little flappers on the side, especially that big one on the right there. See little flappers. What happens is it flaps out at it when he wants to push in that direction, and then as it rotates around, the flapper goes back in. So it's sitting there flap, 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 and basically pushing the bit in the direction you want to go. Drilling data analytics is a big one, and I'm seeing a lot of this right here. There are many sensors, both downhole and surface. A couple of these right here on the pictures are ones that I've taken on the surface of the indication flow shows how much flow is coming out, the weight indicator, how much force you're putting on the bit, as well as how much is on the rig, how fast are you pumping, which says something about your flow rates, how fast you're rotating. There's a little sensor for measuring that. Being able to do that and measure that, as well as downhole, as already mentioned, has been useful, because then you can measure and present this in terms of visualization. These are the current visualization techniques. You can see it's by linear charts and as well as digital outputs and so forth. Typically, these things are push button that you can do. And what's kind of useful about this is, as I mentioned, you can record this and then transfer that data to wherever. So you could be halfway around the world, pull out your phone and dial into whichever company you're using and be able to see what's happening on your rig in real time. Pretty amazing. Only thing I have a issue with, and this is something I know the industry is working on, and that is keep hackers from being involved, which is cybersecurity. That's a big area that I think it needs to be done. But, you know, it was kind of, as I mentioned, you could sit there and watch these things in real time. What you could do is you could actually set up an office somewhere and have very experienced subject matter experts being able to watch a whole series of operations going on, whether it be for drilling or production or stimulation or whatever. These are called real-time operating centers. They were very important. I'm starting to see them kind of slough a little bit. Instead of being physical, especially with the post-COVID times, people are just doing it from home, where they can actually monitor what's going on in real time. Here's an example of a real-time drilling, directional drilling. You can actually see where they're measuring what's happening. You've got the depth, got the time, the tool face, which is not an insult. It's basically which way is a bit pointing, is 60 degrees, which means it's kind of going up and to the right. Kind of gives you all sorts of information about what's happening while you're drilling there. So you use this data. What am I going to use this data for? Well, there are a thing called mechanical specific energy. Imagine how much energy does it take to break a unit volume of rock? Basically energetics. And if it was perfect, it'd just be the compressive strength of the rock. So if I got 10,000 PSI rock, I'd have 10,000 PSI worth of energy that I would use. Well, that's not quite true, but it's close. Here's an example where the ROP is affected by the weight on bit, which is part of the mechanical specific energy, as well as the RPM. And you can see your rate of penetration for 80 RPM versus relatively high weight on bit. You've got a lot of energy in there. And that energy basically shows how I'm pushing into the system and making the operations faster. And what I can do is I can look at this weight on bit and ROP and that mechanical specific energy and determine whenever you see it dive off of the linear trend there, that orange or the red line, that's an indication that there's something going on that's limiting me. And in fact, by using drilling data analysis, I can analyze what's limiting me and then say, okay, I'm going to redesign the system so that I eliminate that. And then when I get back to drilling again, I will drill faster. And then I reach another limiter and then I continue to do that operations until I can get this thing going as fast as possible. That is what drilling data analysis, among many things, does for you. So here's an example of the MSE. If you look over here on the right, you see that MSE trend versus the depth on the left there. You can see the other operational parameters. Notice that the energetics are increasing as you pass 11,100. Why? The bit's wearing out. You can see the bit's wearing out, so they say, oh, time to change our bit. And so they change it to a new bit, and you can see the energetics are far, far better in terms of less energy per unit. Another example of vibrations. When things happen downhole, and here's a start to vibrations and all that kind of stuff, that's a lot of energy being wasted. That's not going into the rock penetration. It's going into moving all that equipment downhole. So by changing the RPM, changing the weight, doing other things like that, you can basically eliminate those vibrations or at least minimize them. Or in this case, they actually broke the bit and had to pull it out of the hole. What you can do is develop what they call set points. Set points are at what is the perfect RPM and weight on bit that I should have to give me the best energetics, which means basically the lowest mechanical specific energy, the lowest vibrations, the highest ROP. By doing this analysis, you can actually figure out, oh, maybe I should be a little bit lower. The RPM looks like it's okay, but maybe a little bit lower weight on bit allows me to be able to drill better. So doing this drilling analysis, like this heat map right here, is a perfect example of where I might be able to do better. Because when I look at the other issue in drilling data analysis, it's like when I'm drilling, that's productive because I'm creating a wellbore. When I'm running casing, that's productive, even though I'm not drilling, I'm still creating a wellbore. But if I lose circulation, if I stick my pipe, if the wellbore collapses in on me, I take a kick or whatever, these are called non-productive times. And if you can basically define them, good luck on that. Sometimes that can be challenging. The idea is to minimize that. So like, for instance, if I have a lot of lost circulation, like we see with geothermal wells, if there is ways that I can minimize that, that's less wasted time. Time is money. And so you're starting to see where we spend a lot of effort looking at the drilling data and trying to figure out, okay, at what point should we be looking at, does it make sense to really spend our time on sloughing shale? Well, not according to this. We're only getting like, 0.1% of my drill time, but it does say that lost circulation is about 3.2% of my time. That might, stuck pipe is another problem. So these are things to look at. So drilling management, one of the things that we look at is define key performance indicators or KPIs. By doing that, you can say, okay, what am I wanting to improve? Say, for example, ROP, and I might warn you, there are a lot of interpretation with ROP. You might say, well, that's just how fast you're drilling. Really? Minute to minute? Second to second? Are you talking about rig to rig? Are you talking about spud to rig release? What are you talking about for ROP? And the same with NPT. That's a tricky one to define too. I mean, it is what, is slow drilling or is that NPT or is it just part of the drilling operation? That's a good question. And so, one of the things what we look at is we spend on what we call days versus depth. And you notice those areas where it looks like it's kind of flat, a lot of times that one might be defined as your NPT. What I did, this is part of a report we put together for NREL on geothermal drilling. And what was interesting is you can see the efficiency of petroleum drilling versus geothermal drilling. And a lot of the flat times that you see there for NPT are lost circulation events. So what does that tell me? I've got to manage my lost circulation on these geothermal wells, among other things. So there are a couple of, many different technologies or management techniques that are out there. One, I'm going to mention two of them. J. Ford Brett, who is president of Petroskills, defined something called perfect time. Basically, based on your rig, how fast can you drill a hole? How fast can you get out of the hole? How fast can you do casing and cementing safely, environmentally benignly, based on the physics of the situation? And the perfect well would be one where the actual well drilling time divided by this perfect time approaches 1. Basically, it's a way to kind of look at how close are you and what do I have to do to get better at that? Another one is called the technical limit. Basically, it is expecting human expectations, hopefully not your biases and all, but it supposedly describes an ideal standard of drilling given site specific, like you're here in Wyoming, or you've got a perfect team, you've got perfect drilling conditions, you've got perfect tools and so forth. The idea is that technical limit is how fast can you drill if everything goes right? And this evolves and you must continue to update it and so forth. One thing I find very interesting, and John DeWard, who is a good friend of mine, been working on this area, and that is to be able to identify different aspects of lost circulation, lost times. So for example, you've got conventional lost time or NPT, that was how we define it. But there's also this what they call invisible lost time. Imagine if it takes you, say, 5 minutes to make a connection because the devices that you're using are kind of clunky. Wouldn't it make sense to be able to improve that so that you can make a connection in 3 minutes? That 2 minutes is invisible lost time. You wouldn't see it, but you can kind of visualize it in the invisible lost time. And you've got what they, when you start looking at actual well durations, you got the best of the best, and then the best in class. Best of the best is like within a field, this is the best one we've ever done. We should be able to hit that one every time. Best in class might be the types of wells that you're drilling. The technical limit is down here where you kind of eliminate as much invisible lost time and NPT that you can. And then the maximum theoretical performance is down there when everything goes right. Well, good luck on that. And then of course, right down there is where you instantaneously create a borehole. And in that case, you would not be going to the Colorado School of Mines. you'd be going to the Hogwarts School of Mines, because that's the only way that's happening. So let's sum up everything that I've mentioned today. And that is, I think rigs will continue to improve. They have to. You're seeing a lot more improvements. You're seeing them, the technology is being developed, improved, changed, and so forth. The way I kind of see it is that rig automation will continue to grow. If you're interested and you're part of the Society of Petroleum Engineers, join the Drilling Systems Automation Technology section. You'll learn far more about rig automation in that, that's where the state of the art is. It's very fascinating. There are other technical sections in the SPE that you might be interested in also. But I see rig automation continuing to grow. Is it challenging? Absolutely. Is it difficult? Yes. But there are roadmaps out there, and I encourage you to go hunt them up. Bit design and drilling technology and processes will continue to allow for faster drilling. It's amazing the changes that I've seen. I remember was out on a rig a couple of years ago, and I noticed the top drive was like coming down. I'm like, good gravy, are they tripping? No, they're drilling. Amazing, amazing type of stuff. And it's all because they got the right bit design for the right rocks. They got the top drives, they got the mud motors and mud pumps and the directional drilling equipment and all just humming in there. So what does that mean? Shorter location times, which is in essence, basically, when you start thinking about environmental impact, this is basically, if you're drilling a well and it takes you 2 months versus 7 days, which one is going to probably be better? The 7-day well. Get longer laterals. In other words, right now, 10,000 feet is pretty common. 15,000 feet is pushing the edge of the envelope because of friction issues and so forth. Could it be 20,000 feet? Maybe more. Who knows? And maybe we might even get 2 MAD wells, that is 2 mile a day wells. Who knows? Management processes will be enhanced. You see a lot of this if you go to conferences around the world in drilling and so forth. A lot of companies have developed using drilling data analysis to be able to come up with better ways to manage it, because data sensors and an analysis of that data sensors will advance. Data sensors right now are probably one of the limiters on drilling rigs because they have to withstand a lot, and the sensors are not picking up great data, but they're useful. And I think drilling data analytics will uncover insights that will improve operations that we never thought of before, never been able to come up with before. I think you'll see that as time progresses. I know here in academia, where I'm part of, we do a lot of this kind of figuring out what's going on and so forth. I've been working with NREL on a project on that. Very fascinating to see. NPT rates will continue to be reduced, approaching that perfect well condition to be able to do the best job that they possibly can. And I do believe the societal and environmental impact will continue to be mitigated as time progresses. It's been a lot of fun. I really appreciate being able to share my thoughts on this and what I visualize the future may bring as we drill into the future. And as I would invite any questions I can answer, or I can question any of your answers, whatever you wish. So with that, thank you very much. And John, how do we go from here?
Hey, so first, thank you, Bill. That was incredibly interesting. And just, again, a fascinating introduction, fascinating presentation of drilling into the future. And I've had a couple questions given to me that as a result of listening to you here. And I see one in the chat pod I will get to here in a moment. But in the meantime, though, I'll ask you all, we do have a few more minutes for questions before the top of the hour. If you'd like to ask a question of Dr. Eustes, please put it down in the Q&A pod and we'll get it asked. I'm going to read this, Bill. Maybe you have access to it as well. I haven't reread this. I haven't read this one over first. It says, one topic that was not discussed today was cementing into the future. The industry is, at this moment in time, seeing the shift from API Class A cement to Class L blended cement, while at the same time, the construction industry is seeing their ASTM C150 type cement being changed to a blended cement type. Now, there's a lot of acronyms there. Do you have any insight into concerns related to these cement changes? And how might we make analysis today on how these new cements will perform in the future?
That's actually an excellent question. I hadn't put cement in there because I hadn't seen a real change in cement for the last 200 years. I mean, we're still using Portland cement, for goodness sake. I do know, I think it was one of the labs, God, I can't remember the name of it. It's one of the hazards of getting old. But the lab up in Argonne, is it Argonne? I think it's Argonne, in Chicago. They're doing some cementing tests and improving cement operations. You're right. I've never actually heard of this Class L. I'm going to have to look that one up. So thank you for sharing that information with me. I've never heard of it. So I can't answer that one because I've never, that's, the thing about doing these webinars, you learn too. But it's, I do think you're right. I think the issue of actually sealing the annular bore between the pipe and the rock is a real key factor, especially when you do fracture stimulation. I've seen cases where the fractures tend to migrate up and down the pipe and so forth, just within the formation. Typically, you don't see it go back to the surface by any stretch. But that's a really interesting question. I'm just going to have to waffle on that one because I don't know the answer. But by golly, I can find out more. I got to learn more.
That it's interesting, Bill, because I had a question come to me about a week ago, very similar to that, saying that starting in August, Ohio's main manufacturer of Class A cement is ceasing production, and they're only going to manufacture a Type 1H, and which is not API approved. So I think they were getting asked for approval to use that type of cement, and based on your answer, I'm guessing it doesn't sound like there's a lot of information maybe that's out there to answer something like that.
No, it's not that, unless you're very specific, like you work for Halliburton or Schlumberger or BJ, whomever else is doing the cementing. Frankly, the cement is kind of a stepchild, and it shouldn't be. It's a real key part of the wellbore construction process. You better have good cement, or you're not fracking, you're not sealing, you're not environmentally benign. You've got to have good cement. And I do think that that's something that I'm not seeing a real high tech sweep. It's not as sexy, if you will, as this thing right here. And that's a very good point. I like that. I like that point. Like I said, I'm gonna have to study up on that one. I'll add a slide in the future for this.
Okay. Here's another question, Bill, from our participants here. James, what's your experience with naturally occurring radioactive material in drilling material and fluids from wells?
That exists. There's no question if you drill rock that has uranium, thorium, or whatever in there, you're going to get it back to the surface. But we're talking about maybe a borehole this big. And if you look at the volume of norms within that, it's relatively low and is it's actually almost non-existent. It exists, but it's not very much. What you typically see norms in is when they build up on the like production wells. You'll see like a scaling, like barite scaling or barium scaling, and typically that tends to concentrate the norms. And the net result is if you trip out of a pipe that's been very highly scaled, you can get some more radiation out of that. But generally speaking, it's very, very, very low and not really a hazard that is considered a big issue.
Bill, if I could impose on you, you told a story about that drill rig in your background picture there. I think that was interesting and relates well to your presentation today. Okay,
yeah, this is an ultra well in the the Wind River Basin, the Pinedale Anticline, and I got a chance to visit that rig. Ultra at this couple about 8 years ago, they were drilling these 14,000 foot S-shaped wells in about 60 days, and by using super spec rigs, better technology, better bits that have been designed for it, they got these wells down to about 7 days. So they went from basically 8-9 weeks to 1 week for drilling the same distance and the same direction and so forth by improving their operations. they were one of the groups that I saw was they were approaching perfect well conditions.
Thank you for that. And Bill, with that, we're going to end today. But Dr. Bill Eustes, thank you so much for joining us and your willingness to come to us. I know you mentioned you made a trip into the office today, so you'd have a good internet. We appreciate your tenaciousness and willingness to do that. So thank you so much. And to our participants, it's always fun to see a bunch of names that we know from past workshops. Or from being on here before. So spread the word, as Dana has up here on the slide. You'll get an email that this presentation is available. If you'd like to share it with somebody, please do so. Thanks again for attending. Go to topenergytraining.com if you want to learn a little bit more about our workshops and training. And with that, I'll bid you all a great day. And Dr. Eustes, thanks again for joining us and making this so great. Appreciate all your.
It's been my delight. More importantly, it's been very great to be able to talk to so many people. This is what I do for a living, and I love it.
Well, we appreciate that you do. So thank you.
Okay.
Have a good day, everyone. We'll see you all again for the next webinar. So long now.
Stay cool.